Let's look at some important decibel factors or relationships. The first one is that decibels are additive. And why do we say that? Well, decibels are related to the log function. And the log function has to do with exponents. So if I have some multiplication 10n times 10 to the m, well, that's just equal to 10n plus n. Oh, I'm sorry, n plus m. So you have this additive part here for the exponents, and the log functions deal with those exponents. So because of this relationship, and you see how things add, decibels are additive. We can just add things together to come up with a final result when it's expressed in decibels. Now, if we have a 10 times increase in intensity or power, then we've just done 10 dB. We've increased or decreased by 10 dB. And we can find that by our formula, beta in decibels is equal to 10 times the log of 10, and we'll say that it could be some power of n. For every increase in power of 10, we just have n here just as a general. Well, the log of 10 to the n is just n, and that gives us 10 times n. So every increase in 10 times the intensity or power is just 10 times the multiple increase or the exponential increase. Now, another factor that's important is what we call half power or intensity. And let's just express our ratio. That our ratio comes up to be 1/2. If you calculate that out, you will find that that's about minus 3.010 decibels. And we just round it to say it's approximately minus 3. Now, along with a half, we can do a double. And that's just taking our formula and having a ratio of 2/1 or 2, and that's just equal to 3.010 decibels, and we just round that to 3. Should write my decibels here so we know what we're talking about. So why is this important to us? Well, let's look at ratios, and just remember that for every double it's 3 dB, and for every half it's minus 3 dB. So let's start with a table, and we'll start out with 1 watt. And it turns out that 1 watt is 0 dB. So let's just say we're going to use power for the moment. So 1 watt, 0 dB. Now, if I go to 2 watts, well, what's my increase in decibels? Well, it's just 3 dB. Now, if I want to go to 6 dB, 6 decibels, I need to double this value, so that's 4 watts. Now, if I want to go to 9 decibels, that just means I double this again, and that would be 8 watts. 12 decibels, double the 8, that would be 16 watts. 15 decibels, that would be 32 watts. So this is our increase. Every 3 dB, we just double the power. Now it works when we're doing minus 3 dB. We just take half of 1 watt would be 1/2 watt, minus 6 dB would be half of a half watt, which would be a 1/4 watt, minus 9 dB would be a half of a 1/4, which would be 1/8 of a watt, minus 12 dB be a half of 1/8, so that would be 1/16, and minus 15 would be half of a 16th or a 32nd of a watt. So you can easily do in your head, if you know the power at a certain point and somebody tells you that the difference is 6 dB, well, you just know that you have to multiply by 4. And think about it from the standpoint of the powers of 2. I have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4th, and 2 to the 5th. So we're just changing the exponent by 1. We're using this 2 as a base because I'm doing double. I'm just increasing by 2 every time. That's just multiplying by 2 gives me the new exponent. If I'm going negative decibels, then that's going to be 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4, and 2 to the negative 5. So we can relate not only the decibels to these values, but we can relate it to the exponent of the powers of 2. It's a nice little conversion, because if I know for every 3 dB I have a difference of 1 in my exponent for the powers of 2, then I can quickly calculate different ratios depending on what somebody tells me. If I know that it's 6 dB, I know that my ratio is 2. Basically, I take 6 divided by 3 is 2. I know my exponent is 2. So it would be 2 to the 4th. It would be a change of 4 times. We're going to do a problem where we can actually use this, and it'll become a little more clear how we're going to be able to use these concepts. Now, table 16.2 is important because it has some different intensities for uh, different thresholds or different sounds. We talked about the threshold of hearing, and that's 0 dB. Yes, that's considered 0 dB, and that's 1.0 times 10 to the minus 12th watts per meter squared. If somebody's talking and we're looking at about 50 centimeters, that's about 65 decibels. Or the intensity is about 3 times 10 to the minus 6th watts per meter squared. Now, the threshold of pain, basically the sound that's going to hurt your ears, is about 120 decibels. It's also about the same for a rock concert. So if anybody's ever gone to a really loud rock concert and your ears are ringing when you come out, that's because that's the threshold of pain. And that's about 1 watt per meter squared. Now the jet at 30 meters is about 140 decibels, and that's about 100 watts per meter squared. This ratio is important for one of the problems on your homework assignment. So make sure you keep that one in mind when you're doing your homework assignment. So these are some important decibel relationships and factors that will be good to know, and not only be useful in the class, but you'll find them useful in your engineering career.